McIntosh. I'm here to sort of talk to you about my dissertation project, my undergraduate. A little bit about me. I recently graduated from the University of Greenwich in sound design BA, creative coder, musician, and media artist. Type this. My primary research interests lie in the investigation of artificial intelligence sensors, application information, particularly and sentiment creation. I'm also interested in other technologies such as virtual reality, augmented reality, AI visual and effective computing. As my dissertation, for my dissertation, I chose to sort of explore the relationships in music and sounds, and the ways that we can capture that information and present it, with to provoke new or mediums for visual in this way. So score visual representation of musical experience. Participant to a piece of music.
You might want to maybe stop your video because your connection's a bit poor. It'll improve the audio.
Yeah. How's that? Is that better?
That's better. That's fine. Yes. Yes,
okay,
we know what you look like now, so we're all right.
Okay. We're running out a lot. How much did you see?
We see your slides, but your video was a bit jumpy, so I think this is fine.
Okay.
Yeah, it looks good to me.
Okay. So yeah, a neural score, which is the image you see on the left, is a visual representation of the affective musical experience. As a participant listens to a piece of music, neural networks analyze their electroencephalographic things to extract information about their emotional response to what they're listening to. This information is then rendered as a graph-like depiction of their complete emotional response to the piece of music. This is a quick example of what it looks like in action. And this is one of the finished images from Moonlight First movement. So the main component of the image, there's the backdrop. The backdrop is the first generated by the system, and it displays kind of a short-term memory of the emotions that are detected, so about 3 to 7 seconds. And the emotions are displayed as a marble of colors on the screen. So in the image on the left, you can see the majority of the image blue, with slight hit of red running through it. This would indicate from the heavy presence of blue that the time would be sadness, so something that's low activation, low valence, but then also the sort of presence of streaks of redness would indicate that you arrived in that blue state from a red state, which would be anger. So someone was angry and then they became sort of more sad, less activated. And then also, if the emotions of the participant are changing rapidly, you would have a much bigger sort of blending of colors, where the main color would be a little bit less obvious and clear, which would kind of reflect the emotional uncertainty of the participant. And then the main item, the neural emotion graph, disk. This is the end element by the system, and it is the complete emotional piece of the coordinates. The emotion graph is presented as a circle that progresses left to right, a counterclockwise motion as the music is playing. And And as the graph progresses, it leaves behind a spectral trail of the participant's brainwave data, the color to which is the emotion that be experienced in time. This design was inspired by traditional data streams such as these and vinyls, but instead of being stored in, it's the emotional that stored. And also the complete analytical of the immediate effect on, whereas the back depicts a running history of emotions. And this is the emotions being drawn all the time. You can see the background on the graphics till it reaches finished. And again, finished images. Provide a modern detailed explanation of what's actually happening, because that was the main point of the project. So it was EEG, so you use a bunch of codes on the scalp read, fluctuation, microvoltages, which are caused by oscillations in the brain from process from neurons, and it suggested that EEG contains identifiers of emotion state such as valence activation. In this project, the Muse brain headband was it's a consumer-grade EEG device designed for meditation activities, but it comes with really good recording and playback tools, and it's quite inexpensive as well, about £120 for the generation model, and it comes with 4 independent channels of 4 electrodes in the position TP9, AF7, F8, and TP10. And then the placement of these electrodes is really good because it gives you this kind of complete spatial signature of the participants' brainwaves, rather than being on one side or front or back one hemisphere. From the EEG and converted kind of spectrum image, in the spectrogram, each color band, so red, orange, yellow, green, blue, represent different frequency widths. So delta is red, gamma blue, and this kind of enables the network sort of stuff to differentiate between the different bands and see them as inside each color banding are the 4 electric positions. More on that later. This method was chosen because it inherently contextualizes the EEG data in both the spatial and temporal domains. So not only have you got the spatial, locality of the channels and the frequency, but you also have this kind of moving window of history of data. And this kind of allows the network to interpret physiological aspects like hemispherical activation, and temporal aspects like spikes and fluctuations over time. The classifications are run in real time with live EEG data, and the generated values are plotted against the circumplex model of effect. Again, more on that later, to produce prediction for the strength of motion felt by a participant at a certain point in time. Then just kind of moving on. So the first band you see, the red one, is the delta frequency bandwidth, and inside of that color band there are 4 individual bands. So you've got the top one, the middle one, the third one, and the last one. So for example, the top one is the back left electrode, the second one is the front left, third is front right, and fourth is back right, and so on and so forth. You've got all of the electrodes and all of their frequency bands in the image. So for action classification, how I actually retrieved information about the participants' emotions from the data are used and called the Russell circumplex model of effect. So a little bit of information about it's recommended in measures of emotion that when approaching emotion measurement, an investigator should base their analysis in dimensions of valence and activation rather than trying to capture emotions as discrete states. So, you know, happy or sad. This concept is further explored in the circumplex model of effect, where it is outlined that emotional valence and activation exist as two discrete systems of the central nervous system. The article further suggests that the intensity of these two systems can be plotted to create a dimensional model of affective experience. And the activators allows an investigator to ground their measurements in two absolute values, so valence, activation, rather than to find sort of arbitrary components and features of individual emotion states like happy, sad, and excited. On the right, you can see the circumplex model. On the y-axis, you've got activation. So activated, relaxed is how intense the emotion is. And then you've got on the x-axis, the valence. So if it's a good emotion, bad emotion, positive, negative. And then the circumplex model of effect is plotting those 2 points to find, you know, a most likely emotion. So to extract the emotion data or information in the EEG data, I used convolution networks. Convolutional neurons are really useful in this because they're able to detect patterns in multi-dimensional data, grouping areas of close proximity. So instead of analyzing the data as one line, standard neural net, they examine it by square. They're quite effective for tasks like image classification, so look at a picture and being able to put in the picture. They're also very useful in applications like this where you're using two-dimensional data. So it's not just a string of numbers over time, it's, you know, an array of numbers over time. Where am I up to? And yeah, it's especially useful in EEG because you can capture those physiological elements such as hemispherical activation. In this project, the library M5 was used, which is a library built on top of the TensorFlow for JavaScript framework. And it was chosen because it integrates quite well into P5.js, which is another library used in the project for the visual element drawing. On the right, you can see a picture from the training of the emotion detection network, or the first training. And then, as you can see, I was obviously quite happy when it structure and pull, flatten output. It's a fairly standard delusional neural net image classification. Once all of that completed, I'd found a way to get this information from the EEG data, kind of repack everything into the alone application. So yeah, and final steps of a standard application was that houses the backend functions of the project. So networks, data processing, OSC role. This application is both lightweight and user-friendly and allows anyone with the same equipment to replicate the experiments in this project. It was created using Electron, which is a framework that allows JavaScript to run in desktop applications through Node.js. It meant that networks receive the EEG data locally using Node OS rather than requiring a bridge program to send the information to the server via WebSockets. These are some sort of images of this is the spectrogram. This is where it is displayed. This would usually, you know, in a real scenario, move image constantly up to facilitate the need. And then classification, which has the model on which has a color in it, moves across depending on classification of valence and activation. And then on that is the instant activation that shows network or the classification network is on the data. And run time, you can have the headset. For this program, it will constantly giving activation for instant activation. You can make a prediction about their motion state. So pro output in OS, it tests both balance and activation values over OS, and the current color, so whatever color is currently also sends out for use in another program. So the system out a classification for both positive events or negative events, and positive activation or negative activation. The system also produced a confidence score for each classification. The confidence score is typically a ranking of how sure the network is of its classification. In this situation, as these are inclusive by classifications, either valence or non-valence, and either positive activation or activation. The confidence ranking can also be seen as a linearity between the negative states. That's kind of held. So just an example of a situation we use this program. This is a node I developed. It's a video game created in Unity called Lundheim. Essentially, a bunch of effect experience-based challenges. And once they complete these challenges, some kind of effect on the audio world around them. So maybe a file or a swarm of bats will appear. The music is also reflective of the motion state. So when the player is more activated and less relaxed, the music is more intense. And when they're more, it becomes softer. And then also the tonality changes depending if there is happy or sad. See on the right, there's a fire element. This will change color to the player's state, and the idea is it has to kind of this to element on the pedestal, and then that state about 10. So I'll play. To make the that I show here that have the emoji backdrop and the graph in them, I used a program called Touch Design. Initially, to use P5, this drawing the spectrums to paint emotional response using particle system flow fields. But this kind of lacked the one-to-one style of data representation I was aiming for. I wanted to kind of a graph-like visual representation of a person's affective experience to music, rather than just a momentary audio visual react kind of thing. So Touch Designer is a hybrid programming environment centered around the Python programming language, and it allows for sort of much easier and more accessible use of 3D element shaders, and it's kind of a lot more suited for this kind of visual work. So the emotion backdrop is controlled by things like the emotion color and the activation value, and the emotion graph is controlled by so the duration, how long denotes the circle. The emotion color obviously changes the color of the graph line as it moves into the raw EG. So this is kind of another example of the Moonlight Sonata. where you can see the changing from blue sort of sad states to light blue calm states. So maybe running on time. I'm going to show all of the results, and these are the images I just produced project for Claireline Rossi, Sonata, first new Rides by Del Rey. In here actually with specific participant provided this quite a large sentiment, sort of sentiment meaning to them. It was actually a song made at their friend's funeral when they were sort of a teenager. So you can kind of see in the emotion graph, it's quite erratic. There's a lot of emotions coming up. And that was kind of a self-parting by the participant, as well as it was a really sort of emotional journey for them. They feel of things come in the airplane. And it's quite for a lot of, with some blitziness and excitement, and more you get the choral breakdown, see more sort of energetic emotion and more intentions. Alkonig is a opera, I believe. It's a very energetic song, the major key, and you see at some points the blue lands where it switches major keys. And yeah, these are the references if anyone's interested. And you can find all of this on my website at www.newofcourse.com, which has all of the videos, all of the a virtual gallery, and a portfolio for further reading if you're interested. Thank you very much.